So we just mentioned that in the nature there is no isolated north and south pole. So the way how people find it out is through a very primitive way. If you have a bar magnet, and people find out, okay, if you have north pole at one end and south pole at the other end, if I try to break the bar magnet into the half, would that be that the first half of the bar magnet will simply north pole, and the second half of the bar magnet will just become the isolated south pole? But people find out that when they try to conduct this kind of experiment, they find out immediately when you break one into two pieces of the bar magnet, this end will automatically generate a south pole and north pole on the other end. And no matter how much times you break the bar magnet, the 4 pieces or 8 pieces, individual pieces always will appear as a pairs of the north and south pole. That's the reason I say that in the nature, we never exist an isolated north and south pole. Now let's talk about the concept of the magnetic domains. So why some materials has their own magnetic fields, but some of them do not? This is related to the properties of the material, but intrinsically it is about the magnetic domains. But you will ask, what is the magnetic domains? So first, we know that no matter what kind of materials, they are made of the different kind of atoms. And I mentioned that in the previous slides, electron will orbit around the atoms, the nucleus. And when the electron orbited around the nucleus, they will produce a magnetic field. The electron within the atom also will spin. They will produce a magnetic field. So therefore, at every single specific regions, how the atoms are oriented will determine that how strong the magnetic fields in that regions. So you will find out in these figures I show you here. So you will find out that in these small regions, most of the atoms oriented to some directions. So this is a magnetic field produced by this part of the material. However, this is just a small part of the material. In these regions of the materials, the magnetic field is pointing to another directions. So if you have a material that at a different part of the material, the magnetic field are all point to random directions, then in that case, we will say this kind of material do not and cannot produce a magnetic field. But intrinsically, it is simply due to the atoms within the material. So what will happen is that if they are all eventually oriented to the same directions, then this material will become magnetized, which means they can produce the magnetic field. So how strong the magnetic field also depends on the number of the magnetic domains. So for example, in this material, now all the magnetic fields are oriented randomly. But let's say that about 70% of the magnetic field are all point to these directions. Okay, so now if you change most of the domain to the same directions, the magnetic fields of this material will be stronger. And if you increase to the 90% of the domain all point to the same direction, they will even produce a stronger magnetic fields. So the magnetic fields, how strong it is, also depend on the number of the magnetic domains point to the same directions. So here is a very clear picture showing what I just said. For some materials, if you try to check the magnetic domain for each of the pieces within that material, if they are all random, then they don't have the magnetic field, so they are just iron. However, if you try to force some of the region point to the same direction, do you see now here they point to this direction, these directions? So more and more magnetic domain point to the same directions. This object start to be magnetized. You have a weak north pole here and south pole here. But eventually, if all the magnetic domains point to the same directions, it becomes a very strongly magnetized iron. So even for the same material, depending on the orientation of the magnetic domains, the strength of the magnetic field could be different. And it is because of this, then this one explained that when you break the bar magnet into two pieces, immediately at one end, you will produce a north pole. Because originally, the north pole will end into the south pole of another magnetic domain. But now you try to separate them. So therefore, immediately, this north pole will no longer end at the south pole of this magnetic domain. So they will behave like a new north pole. So this explains why we see from our previous lecture that when you keep breaking the bar magnet, you never see the isolated north and south pole. Now let's have our second conceptual quiz today. If you have iron paper plate are strongly attracted to, which one of them? So the answer is C. No matter it is a north or south pole, if this material is magnetized, it is always attracted to north or south pole. And also, the reason they are the same and the force should be the same also is dependent on the Newton's third law. Now, I'm trying to connect the two things we have studied together. So, if you have a closed circuit, you produce an electric current. And people find out that this electric current can produce a magnetic field. So this is the first discovered by the gentleman Hans here. So they find out that if you have the long wire current, you will see that this is the magnetic field lines around the long wire current. If you have the loop current, they still can produce the magnetic field. But you can see the shape of the magnetic field is very different. Now if you increase the number of the loops, you will find out that the magnetic field produced will become stronger and stronger. So we are going to study how does the electric current can affect the production of the magnetic fields. So we already learned that any moving charge particle can produce a magnetic field. And the magnetic field formed by the long wire current, the direction of the magnetic field can be determined by the so-called right-hand rules. So let me show you how to use the right-hand rules. So this is the direction of the electric current. So use the thumb as the direction of your current. And now try to curl your forefingers. And the forefinger will be curled along the wire in the counterclockwise directions. So you can see the compass we use here to measure the directions of the B field. You can see here the current is pointing to this way. But at this point, the current is pointing to these directions. And at this point, the current is pointing to these directions. So now they will form a counterclockwise loop of the magnetic field. So the first right-hand rule is that if you have the long wire current, the thumb will be the direction of the current, and the forefinger curls will be the directions of the B field at its different points. And when you flip the direction of the current, which means the current is from the top to the bottom, you are still going to create a magnetic field around the wire. But now the thumb is downward. So when you curl your finger, you are going to produce a clockwise magnetic field. Okay, so make sure that you can use your right hand to reproduce the direction of the B field. So let me summarize. If you have a current upward in a long wire current, the B field is counterclockwise. If you have the electric current from the top to the bottom, the magnetic field produced is clockwise. So therefore, if you are given this diagram, so here it is the long wires, but you have no idea about the direction of current, huh? But now you can see that the current is flowing in the counterclockwise directions. So let's follow the direction try to curl our forefinger along the counterclockwise. Then you will find out the thumb will be the direction of current. So which means for this one, the direction of current is from the right to the left. So from the right to the left, they will produce a counterclockwise current. Okay. So in order to test the understanding, let's try to have the third conceptual quiz. And the answer is both. Don't forget about that. If you have a particle with the charge, they interact with the electric field. And now the moving charge will produce a magnetic field. So they also interact with the magnetic field. So now let's try to study about the property of the magnetic field produced by the current. You can see from the 3 slides below. So if you try to look at from the B to C here, this is one loop current, and this is the B field produced. So if you increase the number of loops, you also increase the magnetic field produced. So therefore, there are 2 ways to increase the magnetic fields. You can either increase the number of the current. So the bigger the current, the bigger the magnetic field produced. The second thing is that if you have this kind of closed loop device, the more loops you created, the stronger magnetic field you can produce. So please pay particular attention to this. This is a very unique property to the magnetic field. It doesn't exist in the electric field. And please also try to build your own picture, how to connect the electric current to the magnetic fields. So to test your understanding, let's have the 4th conceptual quiz. So if you have the electromagnetic, how can you make it even stronger? So when I say make it stronger, I say make it the magnetic field stronger. So the answer is C. You can either to increase the number of the current or increase the terms of wire.